Okay, good evening to everyone who is here and to who is connecting here to this event. So welcome to this event on the Cherenkov Telescope Array Observatory, Eyes on the Most Extreme Universe. So I'm Giacomo Principe, a researcher in astrophysics here at the University of Trieste. And it's my honor today to moderate this seminar, which is going to be where we will learn about what is CTAO, what is the gamma ray astronomy, and how CTAO will help and develop the future of the gamma ray astronomy. And we are going to do that with the three important speakers. But before leaving to them the word and to go into the, let's say, the topic of today, I would like to introduce what we refer about gamma ray sky. So if we can start, okay, with the presentation, you can see here. So the presentation, what is CTAO, and when we talk about so the sky, the universe, every one of us immediately is thinking about what we can see with our eyes. So what is the visible light? What you can see here in this slide is that this is a very nice image, that one in background, that has been taken from the first picture released this summer by the James Webb Telescope. So this telescope, which is the successor of after Hubble, is going to take images in the optical as well also in infrared, but we can see how appears the sky when we look it in the optical band. So we have many galaxies and stars here, and but that's only the part. This is only the visible band you can see here. So the light that we can see with our eyes, but this is only a very tiny fraction of what is the spectra of the light. So this is a much more broader spectrum. And this spectrum, if we think that, so if we compare the visible spectrum, so the visible band, as an octave of a piano, so which has a dimension of tens of centimeters, the entire spectrum of the light is much broader. So it will be like a piano that is 15 meters long, so much larger, and the visible light is only a tiny fraction. And also, if we look at the same picture, so the same source in this case, with different frequencies and energies, so depending on the energies, we can see that the structure is completely different. And unlucky, so you cannot see very clearly here, but I can think that every one of you has already seen this image here on the bottom left, which is related to the first image of a black hole, in particular a supermassive black hole from the radio galaxy, the nearby radio galaxy M87. And here you can see how the galaxies appear if we look at in the radio here on the left, where we can see very well all the jet and the structures. Here in the middle, in particular here, on the bottom, we have the Hubble image, so in optical, where we see a bright emission not only from the jet, but also from all the stars around and the rest of the galaxies. And while at high energies, so in particular in the X-rays here with Chandra-Nustar, and gamma rays with the Cherenkov telescopes and with Fermi, this source appears as a point due to the very low angular resolution, but this means that this source is visible also at gamma rays. So we have a broad view of our single source in order to understand this. So it's like enlarging all the colors that we can see with our eyes. And if, particularly, if we consider the entire sky, so here you can see, okay, the optical, sorry, this went directly to, I should go back. So here you can see the optical sky. So how we see the sky with the Gaia telescope. More or less, that is the image that you have when you look at the sky when there is a very dark and clear night. And you can see all the stars around the Milky Way, so our galaxy, which is very bright in the middle. And also, if you're lucky to have a very dark night and in particular places, I can say you that at least I have seen it like in the Canary Island. You can also spot some clouds in the galaxies. And that's how our galaxy and also the sky appears in the visible light. But this can be completely different if we move to other bands, like at the radio frequencies. You can see here that the emission is much brighter, not only in the galaxy, but we have some structure around. While if we move to infrared, the sky is completely dark, apart what we have in the galactic plane, so our galaxy. And moving toward higher energies to the X-rays, you can see that our galaxy instead is quite dark, is not so bright with respect to other structure like this extended structure that we can see that starts from the galactic plane and goes toward the northern and southern hemisphere. And finally, also to the X-rays, to the gamma rays, sorry, where we have here with the Fermi telescope, we have this nice picture where you can see that we have a bright emission from our galaxy and many point sources around in all the sky. So you can already start to understand that the picture of the sky changed completely. And what we can see with our eye is only a very tiny fraction. So here is just a more complete picture of the sky at different energy or frequency, moving from the top left to the bottom right, from high to low energies. But as I mentioned, so the visible light is only a very tiny fraction. And in particular, if we convert to numbers, so not only about talking about the piano, this very long, 15 meters long piano, if we make a comparison. But if we look at the numbers, so the wavelength that we can see for our optical emission is around hundreds of nanometers. And it's only, as you can see, a very tiny fraction with respect to the long spectra that we have, so the broad spectra that we have for the light, which starts with the radio, which have a size which is similar, so it's a few meters or even hundreds of meters, so a size like a skyscraper, which emission can be also emitted. We have many sources here of radio, like antennas for TV or also for your mobile phone. While if we move toward higher energies, so we have a millimeter with the infrared and for example, your body. So our body is producing infrared, but if we move toward higher energies, so we have X-rays and then gamma rays, which can reach, so the size is small as 10 to minus 20 meters. So is even smaller than the nucleus of an atom. And that emission does not come from our Earth. So there is no source of gamma rays in our Earth. We should look at the universe to special sources to search for these gamma rays. And that's exactly what we are going to talk about in this seminar. So CTAO, this Cherenkov Telescope Array Observatory, is going to observe the sky at this very high energy. So at energies of giga or tera electron volt. This means 1,000, even 1,000 billion of times more energetic than the light emitted by, so the optical light, the light that we usually see with our eyes. And for better learning, so for learning what is the CTAO and to understand how he will change so our view of the gamma ray astronomy, we have here 3 important speakers. So I'm glad to introduce you first, Roberta Zanin, who is the project scientist at the Cherenkov Telescope Array Observatory. Then we have Francesco Longo, professor of experimental physics at the University of Trieste, and Carla Aramo, researcher at INFN in Napoli. I should also mention that Francesco is also the deputy science coordinator for CTAO, while Carla is also the deputy coordinator for the outreach, so for the relation with all the external public. And starting, so to going into this topic, I will leave the floor first to Roberta, asking her, so we just saw how we can, how the sky is at gamma ray energies, but the question is, how can we detect such gamma ray photons, such gamma ray energies, and what is a CTAO?
So, thank you. Good afternoon, everybody. Yes, so I will be talking shortly, describing how we detect these gamma rays. So we have seen that we are at the upper edge of the electromagnetic spectrum, and there is one important thing that we need to understand, that is gamma rays. So that our atmosphere is not transparent to gamma rays, so we cannot detect directly a gamma ray that comes from our favorite astrophysical source, because this doesn't reach the ground, doesn't reach us. So then I want to start the description on how we detect these gamma rays by showing you a video. And then I will describe what happens in the video right after, and then we will look at the video again so that you can see and understand better what's going on. But I think, I mean, usually when we think about how to detect, to look at an astrophysical source, we think about a photon arriving and we detected it. And this, as I said, it's not possible for gamma ray. So let's see what happens. And I hope you see something because there is a lot of light. So I will not describe anything at this stage, no? And then you see that on the ground, there are two telescopes that do not look like the usual dome telescope that we have in mind. But they are different, so they look more like an antenna, if you want to say so, than the usual telescope. So that's, now we try to understand why they look like these and what happened. So you saw that there were a lot of dots, and then at a certain point there was some light that was traveling towards the Earth. So what happens is that when a gamma ray ping the atmosphere, so it interacts with some molecules of the air, and this starts a cascade of an electromagnetic cascade. So a cascade of charged particles, mainly electrons and positrons. Then they decay, they produce gammas, so photons. So this is true. So this is correct for gamma rays, but it also, we need to take into account that not only gammas arrive to the Earth and enters our atmosphere, but our atmosphere is bombarded by charged particles that comes from the universe. So these are the cosmic rays, and these charged particles in turn produce a cascade of secondary charged particles. So you see here that we have the I don't know, do you see the, yes. So you have here the electromagnetic cascade initiated by a primary gamma ray, but you have here on the right a cascade initiated by a cosmic ray. You see that the type of particles that are produced by these what we call hadronic induced shower are different. So they include also pions, kaons, other kind of secondary particles. And what is important, you will understand in a while, is that there is one special particle which is the neutral pion that decays in gammas. So this basically means that there is a pion, all pions starts an electromagnetic cascade that is totally indistinguishable from the electromagnetic cascade which is induced by the primary gammas. So here we are saying that so in our atmosphere there are many of these showers of charged particles. And what we want to look is just those that are initiated by the gamma rays that come from the source that we want to observe. So we need to find a way to identify which of these showers belong to the astronomical source we want to observe and to study, keeping in mind that the ratio between a gamma ray induced showers and cosmic ray induced showers are basically 10,000. So there are 10,000 more cosmic rays than gammas when we want to do. So it's quite a tough work to do, and this is what I will describe in a second. So one important point here, you see the development. So this is a simulation, how it looks like a cascade induced by a gamma ray and a proton at the same energy. So you see that the development of the cascade is very different. So one is much broader than the other. And another important point I want to make is that these showers basically originate, let's say, few kilometers above the sea level. So even those showers, if we are at the sea level, do not reach the ground because they fade away, let's say, at some, let's say, 5 kilometers. So this means that we cannot use these showers directly to detect the primary gamma rays because they don't reach us yet. So then, fortunately, these charged particles that travels through the atmosphere, so these secondary charged particles, are traveling in the air with a speed which is faster, higher than the velocity of the light in the air. So, and when doing this, they produce a special radiation, which is the Cherenkov radiation. So here you see an image of Cherenkov radiation. It's a bluish light, meaning that it is visible light. So what we are going to detect is this visible light, so this Cherenkov light, which is produced by the secondary particles that are induced by the interaction of our gamma ray with some molecules of the air. So it's a pretty complex process that we need to understand why the telescope are done in this way. This Cherenkov light, it's really something which lasts few nanoseconds. So it's something that our eyes cannot detect, cannot observe, even though we can detect visible light because they are too fast. So it means that we need to have an optical detector, but with a very fast electronic to be able to actually detect these super fast flashes. So now I let you look at again at the video. So here you have the primary gamma rays, and you see that this is the cascade of secondary particles, electrons and positrons. And here is when they start producing this Cherenkov light, which is a front of light that travels through the ground. This light is collected by large reflector surfaces and then focalized into a camera. So the reflective surface are basically mirrors, segmented mirrors, that focalize the light, this optical light, into a pixelized camera. So these are PMTs, photomultipliers, or a silicon PM, but this is a detail. So we have detectors at the focal plane, here where there is the camera, and this detector is able to actually image the shower. So what we see is something like this. So these are all the pixels of the camera, and you see here the image of our cascade. So it's kind of something like an ellipse. And by looking at, by basically counting the amount of photoelectrons, one can reconstruct the energy of the primary gamma ray. And by looking at the by looking at the major axis of this ellipse, one can reconstruct the direction of the primary gamma rays. So basically, it's all indirect reconstruction of the properties of the primary gamma rays. So now there is one point which is important. So here you see again that we have this. This is the image of one gamma rays at 300 GeV. And this is the ellipse I was mentioning with the major axis, and this is an image produced instead by a proton at 1 TeV. So you see that the image is very different. We saw before that the development so the proton shower, proton-induced showers is much broader, and you see it exactly in this image. So what we need is an algorithm, a software algorithm that tries to identify which image looks like to be produced by a gamma rays and which one is instead produced by a proton, by an hadron. And this is where, so now the success of this technique came together with the software, so with the technology development. And this is where machine learning that nowadays everybody is talking about is playing a major role, because it's through neural network that we can really identify the nature of these primary particles. The other important point of this technique, so this is basically to say how the technique works. And as you saw in the image that also Giacomo was showing while talking about the Cherenkov Telescope Array, there are many telescopes. So now we see why. So if you have, let's say, more than 2 telescopes or 2 or more telescopes looking at the same shower, so it means that you have a certain amount of images of the same shower. And then what happens is that you can reconstruct much better the direction of the primary gamma rays by intersecting the major axis of these ellipses. So basically you increase the angular resolution and also the background rejection power by using the stereoscopic mode. So this technique has been used successfully. Nowadays, there are 3 generations of what we call imaging atmospheric Cherenkov telescope. So one is in the Canary Island of La Palma. This is the magic telescope where Italy is deeply involved. And nowadays we are moving towards the construction of the next generation of this kind of facility. And this is exactly the Cherenkov Telescope Array Observatory. So you see here, this Cherenkov Telescope Array has many telescopes. So why do we want to have many telescopes? The currently running facilities of this kind have about 2 to 5 units of telescope. And then when you have only this amount of telescope, then you can reconstruct events like these ones that fall exactly on top of the array. But you totally miss events like this one. So you can badly reconstruct events like this one, you miss this one. These are all missed. So in order to be able to increase the sensitivity, so the detection capability of these events, one wants to multiply the number of telescopes. And then in this way, you can really reconstruct a large amount of events in a much more precise way. So that's the reason why when scientists 10 years ago start, or even more, 15 years ago, start to think about the next generation that conceived the concept of the Cherenkov Telescope Array, basically started from an array with a large amount of hundreds of telescopes of this kind. In the design, it was already foreseen to have 3 different types of telescope, the small one, the medium, and the large size telescope. And each of these, basically, let's say in first approximation, what changes more is the size of the primary reflector, the mirrors, the reflective surface. So the larger is the reflective surface, the lower is the energy of the primary gamma ray that I can see. So this is optimized for the lowest energies. On the contrary, the very energetic gamma rays produce a lot of Cherenkov light. So we don't need large mirrors to detect this Cherenkov light. But instead, we need many telescopes to have a large array, because the statistics of the gamma rays decreases a lot with the energy. So we need to have really a large footprint to be able to detect tens, hundreds of TV. And this is where we have the small size telescopes. So the design of CTA is basically an array with 3 different telescopes. So we have a few large size telescope at the center, then we have the workhorses medium size telescope around them, and then an outer ring of small size telescopes. So here we are covering, to give you an idea, a 3 square kilometers area of array. CTA has 2 sites. One is at ESO, in the European Southern Observatory in Chile, and is looking at the southern sky, whereas we have a northern array, which is looking at the northern sky in the Canary Island of La Palma. So here you see the large size telescope. These are the currently operating magic telescope that I have mentioned before. So the CTAO, CTA Observatory is fully funded now in its initial configuration that foresees 4 LSTs and 9 MSTs in the north, and then 14 MSTs and 37 SSTs in the south. So I stop here. Basically, I want just to last two things before finishing. So the CTA is really an observatory. So it's open to the community. So any scientist in the world can apply for observing time and will get in return not only raw data, but already reduced, calibrate, and reduce data. So what you will get is something like what Fermi-LAT, the satellite, provides. So what we call the science-ready data, and then a set of analysis tool that will allow you to produce the final plots that you need for your research and publication. So as Giacomo mentioned, CTAO, this observatory, is starting its construction phase soon. So the funds are secured now. Now we are in the process of establishing the final legal entity, what it's called the European Research Infrastructure Consortium, that should be in place next year. And after that, the construction will really start. So now you see in the south, we're building roads. So we need some roads to reach the site. So we're still far away from having the first scientific results. In the north, so there is the first prototype that is already there, the LST-1, that is already taking some good gamma ray data. And I stop here.
Okay, I would like to thank Roberta for her presentation, and I think we can move forward because we have already seen how difficult it is to observe gamma rays and what we need. So many, not only such big telescopes which have a size of decades, so even 40 meters, as we have seen, can reach the height of the LST, so the larger telescope. But we need several, so many of them. So it's something that it's very challenging. The point is, I would like to ask to the Professor Longo, so to Francesco, why do we build CTAO? What are we going to observe with CTAO?
Okay, thanks, Giacomo, for the nice introduction and the questions. So I think that now that we have seen how difficult it is to detect this light, this very high energetic light, it is worth asking why the scientists are searching for this light, which are the sources that are emitting this light. Because if you are looking at the sky, you don't just want single photons to come from somewhere, but you want to identify photon. As Roberta said, this technique is in place since 50 years or so from different telescopes, but some of the very nice results were produced by the actual generation telescopes. And this in this picture that you have here, I hope that you can see my mouse, my laser pointing. This is one of the HESS telescope currently operating in Namibia, in Africa, in South Africa. And here you see several sources around the galactic plane. So the galactic plane is full of very high energy sources. Now we'll try to see which are the sources that I can bet that CTAO will find. If we are going to meet again in 2 to 3 years from now, I hope that we will see some of the first sources detected by the CTAO, but some of them I cannot bet, and you will understand why. Some of them are still, let's say, I don't know if they are sure, but some of them, most of them are that I'm going to show are sure that we will for sure detect them. So let's proceed now for the different telescope. This is the current situation of the very high energy sky. This is called the TEVCAT. You can find it in this website. There are different colors. Each of these bullets is a source. You see how many they are. They are not so many in terms of total number, but there are around hundreds of sources. These red points are so-called active galactic nuclei, like the one that Giacomo showed in the beginning. In the galactic plane here around, there are a lot of sources. Some of them I will show in a moment. And there are several other types here and around. I will discuss some of them. This is the current situation. So on the basis of the current situation, CTAO will go more deeper inside several of these sources. So let's look what they are. So this is the current situation of the galaxy. This is the same picture as before, taken by HESS. And you see that already in the galaxy, there are a lot of structures. So let me start from here, from below. I hope that you see from here. You see that there are sources that are round shapes. Okay? Also here, there, down there. These are a certain type of sources that I will show in a moment. There are explosion, the remnant of explosion of a massive star, what they are called supernova remnants. Many of other sources here are also related with the death of massive stars. They are called pulsar wind nebulae, where the remnant of an exploding star is powering a nebula of energetic particles. These are the majority of the sources that has detected. And then there is a fog of very high energy photons all around the galaxy, maybe from still unrecognized sources. This is the actual situation. So let's see some of these sources. So what the CTAO will do? We'll do these three main topics, where, as I told in the beginning, probably the first two topics are more sure, more, let's say, we are kindly confident that we will detect them, while the second one is a frontier. So we are not still sure that we will detect it. So first of all, CTA, the Cherenkov Telescope Array. Cherenkov means the Cherenkov light, and the array is what Roberta discussed. Surely will study the cosmic particle acceleration. So where the particles that are traveling around the cosmos are coming from. And most of them are accelerated again by this explosion of massive stars I was talking about. So we are studying the sites where the particles that are reaching the Earth are accelerated. If after the conference you want to come to visit the INFN and INF, let's say, stand in Piazza Unità, you will see the particles reaching the ground, because some of them are so energetic that we can indeed detect the particles, not the photons, but the muons generated by a cosmic proton hitting the atmosphere. Of course, these are where the particle accelerated, but also we want to study some extreme astrophysical environments, like the region nearby the center of the galaxy where massive black holes are hosted, or indeed directly the explosion of the stars. These are called, let's say, for example, the active like nuclei or the gamma ray burst I will be talking about later. And then there is the frontier of fundamental physics, such as probing the nature of dark matter. Dark matter is a component of the universe that is not being yet detected, which is its nature. And the CTAO might help in detecting this nature. So let's see some of them. Let's start with the pulsar wind nebulae, which are the first and the most numerous sources in the galaxy. What they are they? This is a typical pulsar wind nebula, the most famous one. It is called the Crab Nebula. It's the nebula at the center of the Crab, let's say, constellation or something. It is the remnant of a star that exploded in the year 1054, so 1,000 years ago, more or less. It was seen by Chinese astronomers all around. And then at the center of this nebula, there is a pulsar, a rotating neutron star, so a dense star, that is generating some winds of particles that energize the nebula all around, and this emits in all the wavelength. This image is not done in gamma rays, it's done in optical, in radio, in X-ray, but it is a very bright source also in very high energy. So this is one kind of sources. So sources with particles emitted by a neutron star hitting the material all around. This is one type. The second type are the supernova remnants. Again, this is an image made in optical and in X-ray, where you see that these fantastic stuff where inside you don't see anything. Maybe this star completely exploded, leaving out anything there, or maybe a neutron star that has not yet been detected. It's called Tycho supernova remnant. And you see that at the edges are brighter in X-ray than the surrounding. And we think that also the very high energy gamma rays will come from there. So how we can say that? Because the star that exploded is, let's say, accelerating these particles all around. And when they interact with the remaining material around the star, let's say, the shock, so the interaction between the ejected material and the interstellar medium is kindly providing, in this situation, is providing energy to the particles that then they are accelerated and reach later on reaching the Earth. So this is one example how gamma rays are produced by supernova remnants. You accelerate the particles, okay? The particles are hitting the surrounding, and then through the neutron pion decay, the same process that Roberta discussed before in the interaction of protons with the atmosphere, they decay emitting gamma rays. Or even they can, let's say, interact with dense molecular clouds that Giacomo was mentioning before. So if you see in the galaxy, there are clouds of molecules, very dense. If the particle accelerated by a nearby supernova hit these clouds, they emit gamma rays again through the same mechanism, basically, so pi-zero decay. And this is an image that I like very much from a colleague of us, a Spanish colleague of us, Diego Torres, that now is working in Spain. And here you have a supernova remnants. In black, you have radio contours. These red are all the very high energy contours, and these one are the different energy. So you see the importance of looking at this sky in different energies. These, let's say, color and contour are the molecular clouds excited by the protons accelerated by the supernova remnant. This is for sure a source that CTAO will detect. But also moving to the most unsure territory, you see that if we now study the cosmology, so the universe at large, we know that all the materials that we have been talking so far just contributes to the 5% of the total matter and energy budget of the universe. While dark matter, this matter that has gravitational effects all around, just counts for the 26.8% of the total energy budget of the universe, while still the 68% is completely unknown. So we hope with CTA to shed some light in this dark matter. How to do that? I saw just one image, which I found astonishing in a certain sense. This is the image of the central part of the galaxy in optical, in ISO, as Giacomo was showing, with overimposed an image from a satellite, Fermi-LAT, which is in a nearby energy range as CTA will operating, where the central part, so near the center of the galaxy, there is an excess of gamma rays at lower energies that we cannot still understand what is its nature. So there are several theorists that think that this is an imprint of dark matter. So we hope to confirm this claim with CTAO, and we will see, okay? But this is important to understand how important it is to look at the central part of the galaxy also with CTA. And this is why we are building the telescope in the southern hemisphere as well, because from there we can see the central part of the galaxy, while from the northern hemisphere it is not possible. So now let's go away from the galaxy to more sure phenomena. These are called active galactic nuclei, and are massive black holes, like the one that Giacomo showed, with a huge black hole at the center. The energy that is, let's say, accreted, the matter that is accreted, so eaten by the black hole, energize particles all around. These are accelerated in jets, and within the jet, there are several interactions that can generate very high energy gamma rays. And these are the most numerous sources that the Cherenkov Telescope are currently observing, and CTA will look with more careful attention onto these. So these are several processes, but I just wanted to say that, again, the same processes are there. So if the black hole is accelerating protons, protons can generate pi-zero, and pi-zero can decay into gamma rays. And we see these AGNs only if the jet is pointing toward us. So if the jet accelerated by a black hole is pointing toward the Earth, we can see the very high energy gamma rays. Just 1 over 100 of these sources, or 1 over 1,000, are indeed active galactic nuclei in emitting in very high energy gamma rays. So then the importance of this is that they are accelerating all kinds of particles, and even, let's say, these mysterious neutrinos that we can discuss later on. But let me finish with my favorite source, that, as Giacomo knows, are the gamma ray bursts. These were unsure since 2 to 3 years ago, because they are the death of a massive star that explodes and leaves after it a massive black hole of, let's say, 2 to 3 solar masses, so smaller compared to the previous one. But this also generates a jet, but this is not persistent as the one in AGN, but just leaves minutes or so. So you see a source of gamma rays, then fades away. And these were detected since the 60s in much lower energies. In very high energy gamma rays, they weren't detected. But in 2019, these sources were announced by two Cherenkov Telescope, MAGIC and HESS. And luckily, after 15 years, we detected the very high energy emission from this source, which was really something interesting and really impressive. This is a picture from the Nature journal, which is the most important journal in all the communities. And they made also some claim of or explanation of this, and I will try to explain in a second. So you have the gamma ray burst generated by this massive explosion of, let's say, of a star. Possibly this accelerates a jet. This jet has probably electrons in it, or protons, but in this case, most probably electrons. They emit radiation. These electrons are so energetic that they can give some of their energy to the lower energy photons that the gamma ray burst has emitted. And in this way, they provide some of their energy to the lower energies photons, giving rise to another component in the emission, which is called the self-synchrotron Compton in a technical way, that has this incredible bump that was never detected before. So the importance of this that they last very, let's say, just a few seconds. So this very huge telescope have to repoint rapidly to the direction of this star that is exploding in order to catch this emission. So for example, the LST telescope can steer in 20 seconds. You see several tons telescope moving very rapidly in order to catch this extreme phenomena. And we made this job in the past, and for sure CTAO will detect many of them, I hope. This I can bet. So anyone, I'll bet that for sure CTAO will detect several gamma ray bursts, at least 2 per year. Thanks.
Okay, thank you very much, Francesco. So we understood first with thanks to Roberta, what is a CTAO and how can we construct such a telescope, how we can detect gamma rays. We understood now that what we can see, why we also are building such a big telescope. The point is now, and I would like to ask to Carla, who is volunteering, let's say, who is involved to building such a big so for building such big telescope, you will see there are many people behind, many institutes. And so I would like to ask you who is involved in this big project and how is it possible to build such a big project that has such a big challenges, like also we heard about so observing so many sources and other things. So Carla.
Thank you so much, Giacomo, for this introduction. And yes, I will speak about the CTAO community because to obtain all that we have just heard from Giacomo, Francesco and Roberta, it is important to have a large community of research, technician, and also engineering around the world, because this is a very challenging activity to build this the largest array to detect gamma ray. And to do this, we need all the effort of this large community. How we perform the governing to this large project, the CTA project. The final goal is to obtain an ERIC, as Roberta just said, because we need a European research infrastructure consortium. But in the meantime, we proceed with this CTA observatory. That is an interim legal entity in the preparation of the design and also the implementation of the final legal entity that is the ERIC. How CTAO works? Works in close cooperation with another entity, the CTAC, the consortium that is contributing to the definition of the instrument design and the scientific program. That is very important, this aspect. The CTAO is governed by the CTAO Council, which means that it's composed of a shareholders of from 11 countries and from ISO, one intergovernmental organization, and also as associated member from 2 countries that you can see here. Here you can see the list in this table of all 11 member countries and also the 2 associate member here, Netherlands and South Africa. And you see that in this list, Italy is present through the INFN and INAF. Starting from at the beginning of this council, 2014. And this is very important because Italy is one important of this council member. Then, CTAO consortium include a lot of members. You see 1,500 members from more than 150 institutes in 25 countries. They're a very, very big community. And the scientists and engineers of this consortium devised the CTAO concept, like Roberta said, more than a decade ago, 15 years ago, and have been the driving force for its design. The consortium has also developed the detailed scale science goals, and will be also the responsible for the science analysis and the publication of scientific results of this scale science project that is very important to produce the data production to use for the entire community. Then you see in the map all around the world these these institutes in these 25 countries. Then consortium member institutes will make an in-kind contribution. Without this, it's not possible to construct the CTAO, and will support array construction and also science verification and also operation for the science. Okay, now, how these members just meet? We performed the meeting, a consortium meeting, in 2 meetings in the year. This is the meeting in Bologna in 2019. I like very much this photo. I remember because this is the last meeting before the pandemic stop. And it is very important for this, for our community, to meet all together, to discuss, to present the results, to discuss and to solve and to try to find the strategy to solve the problem that can appear. Then it's very important to feel all together a community, very I would say a community that permit to exchange the expertise, a community of scientists, but also technicians and also engineering. But this happens, these meetings also continuing during the pandemic period. In fact, here you see all the participants in this online meeting in 2021, and a lot of us just discuss using in this way Zoom instrument. That is important. This is the message to discuss. How CTAO can perform the construction of this very big project? It's very important, as I say, the global cooperation among all the community to point a common mission. In fact, it's, as you see here in this slide, a structure of the construction project that is very complex, a lot of things to do, starting from the project management, followed by the science, as Roberta said, and then Francesco said, but also a system engineering and integration that is very important to have engineering inside this project, to observe science and the observation inside of operation, and also to construct the science infrastructure following on the computing and the different kind of telescopes and also a common array elements. That a lot of things to do. Oh, sorry, Then Roberta said that we have 3 classes of telescopes types, and this means that we need a lot of different communities to construct this kind of telescopes. And this community is just devoted to one of these types, but also it's a mix. And to share all the information and all the skills that these communities have. For example, here you can see the community of the large science telescopes. That is a project that the project teams that consist of more than 100 scientists from 10 countries, for example, Brazil, Croatia, France, Germany, India, and Japan, Poland, Spain, Sweden, and obviously also Italy. You see here the meeting in La Palma, in the site of the Nord Array. And you see the inauguration ceremony in the 2018, when the first prototype, the LST-1, was inaugurated. And this very emotional inauguration, because all the team, all the members in the team was there to see the start of these very big telescopes. Then the other kind of telescopes, the medium, also will be built by an international collaboration of institutes like Austria, Germany, France, Brazil, Poland, Spain, Switzerland, and also Italy. Italy is almost in all these kind of telescopes. This will be the CTA's work hours with sensitivity in the core energy range of CTA. That is very important. And the planet baseline for CTA includes 23 in the 14 in the southern hemisphere and 9 in the northern hemisphere. Yeah, you can see some colleagues at work on the camera. And some picture of the prototype and the trucks, like Roberta said just. Okay, then, sorry. Another kind of medium telescope is the SCT, the Schwarzschild Country Telescope. Is a 2-mirror telescopes, and also in this case a lot of members inside the collaboration led by USA members, and also here it's a very big effort from Italy and other countries. Here is the inauguration in the January of 2019 in Tucson in Arizona, and I was there, and was also in this case very emotional. It means just in the lower case of the telescopes. Then at the end, the small size telescopes, that is, will outnumber all the other CTA telescopes with 13.7 planned to be spread over 3 kilometers square in the southern hemisphere. And also in this case, the design is a dual mirror Schwarzschild configuration, and thanks to its small plate scale, using novel camera based on silicon photomultiplier, like in the medium SCT. This effort comes from different prototype that is just merged together in a process named harmonization. And this is at the end, the results of this very good works. Now, what is the role of Italy? Italy, as I said, contributes to CTA through INFN and INAF, and by several universities. obviously also the Trieste University, and making a special contribution both to telescopes, but also to construct, to science and outreach. Italian research technician and engineering are also engaged with coordination rules and responsibility in all type of telescopes, as I said, since the beginning of CTA adventure. But, and more important, with the approval of the CTA Plus project for the PNRR research infrastructure call, it will enable to construct additional 2 LSTs and also 5 more SSTs that we just placed in the south side. In the slide, you see the work breakdown structure of this program, and you see that a lot of works will be due during this the following 3 years in this CTI Plus project. The rule of the construction of this CTA may just getting started, we see, but the excitement surrounding its scientific potential is worldwide, and it's very important because a lot of other people outside the collaboration is involved in this aspect. Then great emphasis is placed on the science and the technology outreach, and also on the dissemination activities with the contribution of 60 members from the CTA consortium, who organize a lot of outreach activity in the school for the general public, citizen around the world. Like, for example, the things that we are here in this very nice science festival. And we use all the available communication channels, the festival, but also from web, so it's social media, and TV, radio, and we perform a lot of and organize a lot of activity among these. For example, I can mention People of CTA, that is just an interview from some member of CTAO, woman of CTA. Here in the photo, see Roberta that speak in this very nice activity, and also some kind of about the diversity, for example, building from diversity. And we perform also a lot of activity from educators, for teacher, for school, and you can find this type of activity on our website, the CTA Observatory. And there is also the possibility to ask for a physics on call, especially for the students, then can ask to meet online, but also in presence, some scientists from CTA. And you can find in the web also a dictionary of extreme universe that is important because just to introduce a few words to understand our physics. Then what to do? I want to finish, show you this nice picture that I have taken when I go in the sites, and thank you very much for your stay.
Okay, so thank you very much, Carla, for the presentation. So I would like to ask, since we have a few minutes more, if there is any question also from the audience, if you have any question that you would like to make to our speaker. And so you can raise your hand, and there is also a microphone here for the question. And maybe in the meanwhile that you, I don't know if there is any question ready. Okay, I see already two, so we can start with your question.
Hi, I wanted to ask, what would be the difficulty of building an array of satellites instead of using a passive way of finding the gamma rays? Like, why not detecting directly, but having to detect the showers?
I say a few words. The first one is that the energy, the higher energy you go, the lower number of photons you get. So in order to catch, let's say, photons of 100 GeV, you have to build such a larger telescope that the mass will be so big that you cannot detect it. So this is why we needed the full atmosphere as the target to detect these gamma rays. It would be nice to detect it directly. So for example, Fermi, the telescope that we were discussing before, is reaching up to 100 GeV. If we need, let's say, a factor of 10 more in energy, we will need a factor of 100 in size, which is impossible to afford in a satellite. And an array of satellites which cost too much, of course, to put it on the crew.
Hello, thank you very much for the presentation. Due to the fact that you work with high energies all the time, I would like to ask you, for you, what means energy? Like, I don't know, please tell me what's energy, because I study physics too, and well, it's a question that sometimes is difficult to answer. Thank you.
I say one word, then I let Carla to answer, because she's more expert. No, I'm joking. Let's say energy in this sense means, let's say, the energy of the photons, the larger energy they have, the shorter wavelength they have. So photons of larger energy means that there are the shortest wavelength. In this sense, very high energy. But we use the energy also in other manner. So these are the very energetic sources. So the more flux of photons they emit a large flux of photons, but also photons of their single energy. The single energy is higher. But in other sense, photon is equal to mass. But we haven't talked about that in the discussion. But if Carla wants to add anything else, I don't know, or Roberta.
I think that this is, yes, the energy, it's very difficult to, yes, also to, I would say, reconstruct also in this kind of telescope. That is one important and the first point that it's important to detect and to reconstruct, but it's very difficult. Then it's one of our most important things that we want to do and also with, I would say, in a better way that we do. Then this is one of our challenge in this experiment.
Okay, if I can make an example, sorry, about this to give you probably a better feeling of what is energy. So the energy is higher is the energy, deeper you can go inside something. For example, if you think about a particle, so like if you want to reach, let's say, the surface, like taking the matter and we take, I don't know, the border of a molecule, then that is quite easy. Let's say we need low energy to reach just the surface of the molecule. If we wanted to break the molecule and look what there is inside, you need more energy. And that's something that you need even more energies if you want to look at the nucleus and so on. And the energies that we were discussing here to have a comparison are energy which are similar or even much more higher than the energies of the particles that are accelerated at CERN at LHC. So there, what is the goal there? Is much more. There, it's let's say it's just a few, so 7 tera-electron volt. Here we are discussing about hundreds of tera-electron volt, but it is that there, how do they do in so at LHC in order to see? So let's say these very tiny particles, which are even smaller, so to disrupt even the protons, what they do, they collect its proton to see even quarks and to search for new particles and so on, like the Higgs boson. But what they need is really to accelerate up to higher energy. So the idea, let's say a comparison with the energy is that you need more power if you want to break something and look what there is inside. That's the idea of energy, that in this case, while here in the Earth, and it's an artificial laboratory to create and accelerate such particle to up such high energies, so tera-electron volt, we need something which is artificial. While here, we are using, let's say, a natural laboratory, which are such sources that also Professor Longo, so Francesco presented before. So such like pulsar, we have from supernova and so on, where there is like shock emission and so on, which can accelerate the particles to such high energies.
Yes, as I can also add about this very big energy, because you thinking about like a ball, a tennis ball that launched like in the very big say match, tennis match. That is, but this energy is concentrated in an elementary particle, not it's a very big macroscopic. That is, it's a fantastic way that we can use this kind of sources to understand and go deeper in the matter, like Giacomo just said. That is a very powerful tool for us. It is very important to detect this kind of a particle, very high energy particle, and to put all our effort inside to build this such a big array.
Hi, thank you for the speech. I have two questions, actually. The first one is how the location for the telescope is chosen, because it seems all very fancy location. And the other questions, I have an engineering background, and what I think it's a problem, or maybe, of course, there's already a solution for that, is the synchronization about systems that acquire the same data from different points in the world. So how this synchronization works, because I understood it's some nanosecond phenomena. So I guess the synchronization is something very, very important.
Okay, so thank you for the questions. First question, first answer. So the question is, sorry, the sites, right? So there are two main points. One is the sky, the quality of the sky, because we're looking at optical light that can be absorbed if the sky is not highest quality. So as you saw, we chose two sites that are part of an astronomical observatory. On one hand, we have the Roque de los Muchachos Observatory, Roque de los Muchachos in the Canary Island. On the other side, we have La Silla Paranal. So these are two sites that were already chosen by the astronomers for the great sky quality. And that's the first point. The other point is that, as I explained, so we are looking not at the gamma rays, but at the cascades and the Cherenkov light. So we did several simulations to understand what's the height of the site, which is optimal to cover the energy range that we want to have. So from tens of GeV up to hundreds of TeV. And the result was between 1,000 and 1,500 meters and 2,000. So this was another parameter, another requirement, let's say, in the site selection search. And so with these two, let's say sky quality and this height, there was a site selection committee that I think was a great job, because they went around the world in the best places, and they checked, so they define some measurements for the sky quality, for instance, and these two were identified. Then on top of these that are mainly scientific, so that they are the most important, there are also other aspects like the political situation of the site. So you don't want to build something in a country that can be difficult to reach for political reasons. So this was another constraint we took into account, and the result was that one. So can you repeat the second question?
Synchronization of the signals.
Synchronization.
Okay, so here what we are looking at these events, these cascades that takes a few nanoseconds, and so there are, for instance, in one of the telescope type has a parabolic shape. So the mirror has a parabolic shape. So that this means that it is isochronous. So we keep the time arrival of the flashes, and then we can reconstruct, let's say, the time gradient of the arrival. And this is another parameter that we can use to to identify the nature of the particles also, and because the time evolution can also be different between the two. But it's not like, I don't know if you are thinking something like an interferometer in la radio, this has nothing to do. So so we are looking at events at this. The telescope can detect the same events, of course, and it is you can identify them either in software, so offline, or hardware-wise with a stereo trigger, what we call the stereo trigger. So either you have a hardware trigger that says yes, that's the event, or you can do it offline. But this has, I mean, it's not. So the precision that you need for the correlation of the events is not super high. It's not nanosecond. But anyway, we have a fast electronic, so gigasample reading out. Yeah.
And this trigger is, of course, done on site. So the north alone and the south alone, we are not, let's say, connecting the two.
Yeah,
the reference.
I would say if there are no more questions, probably we can close here the meeting. So I would like to thank you for participating and coming here. I would like to thank again the speakers. And finally, I would like to invite all of you to come to Piazza dell'Unità. So there is the stand INFN and INAF stand where you can hear more about also the Cherenkov Telescope Array and about other instruments, gamma rays, and so on, the activity about INFN and INAF. So thank you very much again for coming, and enjoy the rest of the day.
And tomorrow there will be a conference just in Italian, unfortunately, on one of the satellite, the gamma ray satellite, which is called Agile, which is operating since 15 years, that is providing the view of the sky at the lower energies, but it is a fantastic engineering, let's say, jewel made by Italy in the past. So if you are willing, tomorrow afternoon, the same time in Piazza Unità, there will be a conference on Agile.